Alright, here we have two disks of equal mass. This one is solid throughout, whereas this one is hollow. We're going to roll these both down the ramp to see which one achieves a higher velocity by the time it gets to here. So we'll be able to tell that by which one crosses this line first. So, 3, 2, 1, wait. Make a prediction. Which one will have a higher velocity? The solid throughout, concentrated around the ring, or will have the same velocity? Got one? Okay. 3, 2, 1, go. Was that what you expected? As we just saw, and you may or may not have predicted, the disk that is solid throughout was able to achieve a higher velocity than the disk with the mass concentrated around the edge. Now, this is basically because the disk that is solid throughout has a lower moment of inertia. And I'll explain what this means in a moment. So, when you look at an object that you're going to try to rotate, some objects are harder to rotate than others, especially objects are harder to rotate that have their mass concentrated around away from the point of rotation, as opposed to objects that have their mass concentrated more close to the point of rotation. So, both of these objects have the same total mass. But with the disk, the mass is concentrated around the outside. Whereas, if it's solid, it's spread evenly throughout. Now, moment of inertia is given by mr squared. Now, m is the mass of a particle, and r is the distance of that particle from the point of rotation. So, because it's m times r squared, the radius of the particle is more important than the mass of that particle when you determine the moment of inertia of a certain particle. You can think of this disk as made up of an infinite number of particles, but those particles all have a higher radius and the same total mass as all the particles in this block. So, with this block, there are particles with the radius anywhere from 0 to the full r value. Whereas in this, most of the particles have roughly the value r for the radius when calculating the moment of inertia of each particle individually. So when you take the sum total of all those particles, the moment of inertia of this disk is much higher when it's hollow than when it is solid. Now, this translates into a higher velocity at the end due to the principles of conservation of energy. When both disks start at the top of this ramp, they're at height h above the ground, and because of this, at the same height h and the same mass m, they have the same gravitational potential energy. Now, as these begin to roll down the hill, that gravitational potential energy is converted into kinetic energy, both translational, linear, and rotational, because it takes energy to move disks down the ramp, and it also takes energy to roll them as they go. So, as we saw, their velocities are different. So, let's start with the hollow disk. It starts out with entirely potential energy, mgh. And by the time it gets to this point, all of that has been converted into kinetic energy. Now this kinetic energy is, as I said, the sum of the translational kinetic energy and the rotational kinetic energy. Rotational kinetic energy is given by 1/2 I omega squared, where I is the moment of inertia, mr squared, and omega is the angular velocity, the velocity of a point in radians per second as the disk rotates. But the translational kinetic energy then, or the energy of it moving horizontally or down this incline, is given by 1/2 mv squared. N being the mass of the entire disk, and v being the velocity horizontally as it moves. So, why is this v higher for this solid disk than it is for this hollow one? Well, it has to do with this I, this moment of inertia. Because if the object is moving at a velocity v, the angular velocity, omega, is given by v over r. Omega is given by v over r. So, let's start differentiating the two. We'll say that this is, the velocity of this one is vd, and this is vc. So, the kinetic energy of the hollow disk is given by 1/2 I of the hollow disk, angular velocity of the hollow disk, plus 1/2 mass. Mass is the same for both though, times now, looking at the disk that's solid throughout,
Omega C and omega D should be squared here.
so now we have an equation for both kinetic energy of each disk as they reach the bottom of the hill. So, when we look at these I's, they're actually given by different equations. Now, I is based on mass and radius. And now you may ask, the masses of the disk are the same, and the radii are the same. But the difference comes in where the moment of inertia of the hollow disk, IC, is mr squared. Because essentially, every particle in this is a point mass radius r away from the center. Whereas I of the disk is given by 1/2 mr squared because the particles are dispersed evenly throughout the entire radius. So, if we plug these in, the m's are constant and the r are constant. This one.
See you guys on Tuesday.
Sorry.
We at school?
And this omega is given by v over r, and that v is vc. These r squareds cancel, and we're left with 1/2 mv squared plus 1/2 mv squared, so mv squared. Now, looking at the disk that is solid throughout, though, this time moment of inertia is given by 1/2 mr squared instead of mr squared. d squared over r squared mvd squared. Simplifying, r squareds cancel. We're left with Alright, so now we know the kinetic energy of the hollow disk and the kinetic energy of the solid disk are given by these two respectively. We've been representing this as kinetic energy of D and kinetic energy of C, but really they're the same. Because as we saw earlier, gravitational potential energy is given by mgh, and kinetic energy is given by these, but energy is conserved. So, as they roll down the hill, the kinetic and potential energy change, but the total energy does not. So when all of the potential energy has been converted into kinetic, the kinetic energies are equal. So, 3/4 mvd squared equals the energy of the system, which then equals mvc squared. The m's cancel, square root both sides, and we're left with vd root 3 over 2 equals vc. And this is actually the ratio between the velocities, but it shows that root 3 over 2 being less than 1 shows that Vd needs to be larger than Vc, so that Vd times a number less than 1 is Vc. So, the velocity of the disk that is solid throughout will be greater than the velocity of the disk that is hollow. Thank you for your time.